Hi everyone, Mr. Lee here. In this video, we're going to go over the period of a pendulum. All right, so let's get a couple terminology out of the way. The term period, we're actually used to this term period before because we actually discovered it when we were going over the unit for time. So period, the variable for period is a capital T, and the units for period is seconds. Now, this is easy to remember because we discovered time before with the lowercase variable t, and the units for the lowercase t was also seconds, or s for seconds. Okay. Now, technically, period, the units for period is seconds per cycle, as I write over here. But usually we think of things as one cycle. Now you might be wondering, well, Mr. Lee, what is one cycle? So you can think of it this way. One cycle is how many repetitions. So for example, we're going to be talking about a pendulum. So if I have a pendulum here, so a pendulum is any object that is attached to a string that is allowed to flow freely back and forth. So one period would be when the object returns back to its original position. So if we let this pendulum go, this pendulum will swing out and it'll swing back in. So when it swings back into its original position, that is what we consider to be one cycle. And so period, or capital T, is how long it takes to go or to complete one cycle. All right, so we're going to get into the terminologies a little bit more with the pendulums and the physics behind the pendulum. But before we do that, I actually want to go over one other variable with you, and this is the variable called frequency. Now, frequency is something that we use in our day-to-day language, where frequency just tells us how frequent something happens. For example, your birthday, your frequency of your birthday is 1 per year. Right? Because that's the frequency, is how frequent it happens. Now, for physics, it's actually the same thing. It doesn't really change. But the equation frequency, it really shows us why this is the case. So frequency, the variable for frequency is a capital F, and the units for frequency is cycles per second. And we came across this before when we're going over the rotational unit. So instead of saying cycles per second, we sometimes said something like revolutions per minute, or RPM. Okay, and so we discovered frequency before, and the units for frequency is cycles per second. Now, if you take a look at this, cycles per second is the units for frequency. It's actually the inverse for the units for period, and our equation follows suit. We can say that period is 1 over the frequency, okay, because the cycle tells us how frequent something is, and inversely, we can say that frequency is equal to 1 over the period. Okay, so we have the equation for period and the equation for frequency. Now, this equation for period, we're not really going to use that as much. This is just like the generic equation for period, but we're going to go into the idea behind period for a pendulum specifically. Okay, get ready. So the period of a pendulum. Now, before we start, I'm going to draw the pendulum once again. So a pendulum is any object that's attached to a string, and when released, because of the effects due to the acceleration due to gravity. So for us here on Earth, we say that the acceleration due to gravity is 9.8 meters per second squared. Okay, this pendulum will be swinging back and forth. Okay, it'll go back and forth, back and forth, back and forth. Now, there are effects that slow down this back and forth motion. We'll get into that later. But the idea is that if you have an object in position 1, it'll swing to position 2, then position 3. So it'll go 1, 2 to 3. And then when it swings back, it'll go from 3 to 2 to 1. And then it'll repeat this over and over again. And this is how we can see that it's actually one cycle because of that repetition. Okay, so it swings out and it swings back in. All right, now from this motion, we can come up with the equation for the period of a pendulum. And we say that the period of a pendulum, so capital T, and we're going to do a little subscript here because there are different kinds of periods that we can go over. One is a pendulum and the other one is a spring. So the period of a pendulum is equal to, get ready for this, 2 pi. And that 2 pi is there because of the graph that gets generated when we are graphing the period of a pendulum, and I'll show you that in the next video, times the square root of, now this is the important part because this right here tells us what actually affects the pendulum itself. And that is L, which is the length of the string, divided by G, the acceleration due to gravity. Okay, so L is the length of the string, and G, of course, is the acceleration due to gravity. Okay, so like before in the previous videos, what I want to go over is exactly why these variables affect things and how they might affect things in your problem. Because at this point, I trust that you can plug this equation into different word problems to come up with a answer. All right, so we have L and G. Now, what this shows us is if the length of the string increases, the period of the pendulum also increases. And this is what we call a directly proportional relationship. Okay, now technically the relationship is a squared relationship because we have the square root, right? So if we wanted to get rid of the square root, if we square both sides, we get period squared times the L. So it's actually a square relationship. But the idea is that if one increases, the other one also increases. Okay, and the other relationship here is the acceleration due to gravity, which is G. Now, because G, or the acceleration due to gravity, is in the denominator, we have this inverse effect. So if the acceleration due to gravity increases, then the period of the pendulum, it decreases, and it's a square, inversely proportional relationship. Okay, it's a square inversely proportional relationship. Now, let's go over why this might happen. Okay, now if we go over the length of the string, so if I were to, you know what, let's do a quick little sketch for the length of the string. If we have a tiny little pendulum here, okay, and this pendulum is able to swing back and forth, the circumference, or the actual arc length that this pendulum has to cover, it's not that much. It's very small. Okay, and so because the actual distance that this arc length is small, the period goes up. Okay, the time it takes, it doesn't take that much longer. Now compare that to if it were to be a really, or excuse me, the period it takes would be really small for this one, right? Because we say that the two are proportional, or excuse me, square proportional. If the length is small, then the period it takes is small, because it takes a fast amount of time. It doesn't take much time at all. But if we compare that to if we increase the length of the string, right? We make this string super long. Now that means this arc length right here, this is a long distance that this pendulum bob, that's what we call the object that's hanging, the bob, it has to travel over a longer distance. So that arc length increases. And so we say that if the length of the string increases, so does the period of the pendulum. And that is also a directly square relationship, or square directly proportional relationship. Okay, so that's the reasoning behind the length of the string. Now, what about the acceleration due to gravity? Now, this one's a cool one. Now, usually this one is something that you can't really test for here on Earth, but it is something that we can theoretically think about, right? And so let's say we have a pendulum of a certain length. Okay, we don't know what that length is, it's just L. And we have a bob of mass M. Okay, once again, bob, also short for Robert, but in the physics term, it's just the hanging mass. Okay, hanging mass. So on, let's say, a planet with a greater acceleration due to gravity, let's say, I think Saturn, right? Or Jupiter. I do know that Jupiter has a greater acceleration due to gravity. What will happen is, compared to Earth, right? Because the acceleration due to gravity for Earth, it's pulling on this pendulum downwards with a certain amount of force, and we call that F of G. Okay, we call that f of g. But if we were to go to a different planet where f of g is bigger, it's going to be able to pull this pendulum with greater force. And so if the pendulum is pulled with a greater force, then it's of course going to be swinging back and forth at a faster time period. Okay, and so this is where the inverse relationship occurs. So if the acceleration due to gravity is bigger, okay, we see that it's an inverse relationship, so the period becomes smaller. Now, sometimes this tricks me up too, because I think that if t is small, then that must mean that it takes a longer period of time, but that's not the case. This is a shorter time, right? The time decreases. It's a shorter time that it takes to go back and forth. Now, this should hold true theoretically if we think about it, because if the acceleration due to gravity or the gravitational field of the planet is so much stronger, then it's going to pull on that pendulum just a little bit more. Okay, it's going to pull it with a greater force, and it's going to allow for it to swing back and forth at a faster period. Okay, now this final little piece right there. We mentioned this idea of the bob, and this is the hanging mass. Now, this is one of those red flag moments. So I'm going to get my galaxy pen, right? This is a red flag moment because a lot of people think, and they still do think, that the heavier mass, okay, the heavier mass will cause the pendulum to swing faster. Okay, aka it'll have a shorter period, okay, because the time will decrease. So a lot of people think this. They think that if m increases, then the period will decrease. Now, this is absolutely 1,000,000% not true. And the equation shows us this. If we take a look at the equation for the period of a pendulum, it's not even there. Mass isn't there. Mass doesn't even matter. Now, one other reason comes true for this, and that is because of the variable that does matter, and that is g, deceleration due to gravity. Because we know that the acceleration due to gravity, or the gravitational field for all objects is the same. Ooh. So this just simply means, like we did a classic problem when we were doing the forces unit, right? If we have a small pebble, okay, compared to a large boulder, okay, so we have a tiny little mass versus a giant mass, okay, and we were to drop them from the same height, assuming there is no air resistance, okay, there is no air resistance, both will fall at the same rate, and we call that rate on Earth 9.8 meters per second squared, deceleration due to gravity. Right? It doesn't matter. It doesn't matter that one is more massive. And the same holds true for a pendulum, because it is the acceleration due to gravity that is pulling these objects. So it doesn't matter if one object is more massive than the other when it's in terms of a pendulum, because both will fall at the same rate. All right. That's it for this video. In the next video, I'm going to go over how to look at this period of pendulum with a graphical eye. Bye-bye.